Hey everybody, I hope this finds you all well. So today I got a couple of comments on the Carver M1.5 amplifier. And anytime I put up a video on a Carver amplifier, people get confused about the type of amplifier that it is. I've heard a lot of people say that they think it's a Class D amplifier. I think they get confused that the magnetic field thing has something to do with the amplifier, which it doesn't. The magnetic field is the actual power supply. Magnetic field supplies are, let's just make it simple. It's a triac-based light dimmer, like what you use to dim your lights in your house, you put on the wall. And it's kind of a modified version of that, where they use a triac to chop up the AC waveform coming in from your mains into a saturable transformer. If you try to hook direct mains into a magnetic field power supply power transformer, you will make it fail because it will drive into an overcurrent mode. And the reason being is the windings, the turns ratio is not the same as you would have on a normal power transformer. It works off of a principle of you're only driving enough signal into the transformer to get the output you need based upon the current that it's drawing at that particular point in time. So in most cases, an amplifier that's sitting at idle current, that quiescent current is very low. It's milliamps. So it'll drive that transformer, at a lower duty cycle. And then as you turn the volume up on the amp and it starts demanding more current, the triac will fire more often and stay on more often, and your duty cycle of that AC waveform will get wider. And it's basically going to not usually go much beyond 90 degrees of that half cycle. So you'll see this funny looking kind of shark fin looking waveform with some noise on it, and that's normal. And as you draw more current, it'll kind of distort a little bit, but you'll see it drive a little bit harder. That's what a magnetic field amplifier is. It's just a transformer that has a different turns ratio and possibly a little bit different permeability core, I don't know for fact, and it has just a variable input drive. Doesn't work exactly like a switching power supply or a switch mode power supply, but it's kind of a predecessor to that. So that's what magnetic field is. It's just the power supply that drives the amp. Now what I want to clear up in this next couple of videos, I'm going to make them short, is what is a Class D, a Class G, and a Class H amplifier. The type of amplifier that Carver is using in those magnetic field amps is a Class G, not D as in dog, G as in golf. So, and it's a completely different topology than a Class D, which is the kind of thing you're used to looking at, like these little teeny tiny. This is supposed to be, if you read it, a 500 watt amplifier, which, yeah, I'll eat my hat if this thing puts out 500 watts true power. But anyway, see how tiny these are? They work off of a modulated pulse train. Like it's a pulse width modulated pulse train, let's say. And then it uses a filter to filter out the high frequency, and it only allows the audio frequency to get out to your speaker. That's how those work. And that's what we're going to look at today in this video. Then in the next video, we're actually going to look at a Class G amplifier, and then I will explain the difference between that and Class H, because they're very similar what they're doing in principle. So if that sounds interesting to you, stay tuned. That's what we're going to look at. So just a little review before we get more into this. I just want to talk about the difference between frequency modulation and pulse width modulation. They're both pretty similar. The main difference is with frequency modulation, the entire frequency will shift, it will change. Whereas with pulse width modulation, the actual time period from one beginning of one waveform to the beginning of the next is fixed. And the only thing that changes is the duty cycle. So I'm going to play an animation here in a second, and you'll see with pulse width modulation, what's happening is as you're feeding that modulation signal into there, the higher the frequency, the faster they're going to squish together or pull apart further. And you'll see that the waveform, though, stays fixed at one point. It never moves. Whereas with frequency modulation, what you're going to see is that the whole waveform will squish together and pull apart. So if you look on the left is an example of pulse width modulation. And if you look on the right, that's frequency modulation. Now, the higher the frequency of your audio or whatever you're using to modulate it, the faster those are going to go. That's a really low frequency modulation right now. It's only about less than 1 hertz. And the further you spread them apart and further you squish them together, that is controlled by the amplitude of your modulation signal. So that's what it is. That's the difference. They both work very similarly, but the one on the left is actually the way that a Class D amplifier is going to work. It's going to take the duty cycle of that pulse and make it wider and narrower. Whereas with FM radio, the entire frequency shifts and goes in and out. That's it. So before we get started, if you go back through my videos, I did an amplifier classes video. And when I say class, I don't mean class as in teaching class. I mean the class of amplifier. Class A, Class B, Class AB, and so forth. And I explained some of this in that video. So if you want to go back and look at that, feel free to do that. But we're just going to focus today on the Class D amplifier. Now, Class D is something that all these cheap Chinese whatever that you buy cheap, they're 200 watts per channel, and they're like this big, and they run off of a little power brick. Those are all Class D, and they work off of this principle. Class D amplifiers are very, very efficient. So they run very cool, they're very small, and can produce a lot of power in a very small package. So all those things are good about them. What's not good about them is the stability that they can have. They don't always like low impedance loads like a 4 ohm or 2 ohm load, although they can be modified or designed to deal with that. They usually don't like crazy reactive loads like a speaker that has a really elaborate crossover in it or something. So you kind of have to watch those things, but something that you would see in a car radio or a Bluetooth amplifier with a set of speakers on it, they work just fine. But anyway, they're a very simple concept. If you know how an FM radio transmitter works, you pretty much know the principles of how this is going to work. So what you have is an oscillator, and it's going to set up a pulse train of little square wave pulses. And in this case, let's just say it's 200 kilohertz. They're usually going to be higher frequency like this. And usually in the hundreds of kilohertz, although some of the high-end ones that are very expensive, not like the Chinesium ones you get, they actually can run up in the megahertz. Now, there are ones that do that, but to do that, it gets exponentially more expensive and complex to get that all to work properly, but they do exist. So let's just talk about the 200 kilohertz. So you have an oscillator, and you can modulate it. You can modulate that duty cycle. Okay, and I say it's FM, but it's really not frequency modulated. You're actually changing the pulse widths. And by changing that, you're modulating the pulse width, which is kind of the same as frequency modulating, I guess, in some ways, but not. You're creating two signals coming out of it. You'll have the original fundamental signal, and then you'll have the modulation. And what the idea is you get that to come out, you go through a low pass filter and you filter out the high frequency, and you only let the modulation content come through. So in this case, your modulation is being done by your audio source. So you drive that into there, You vary that 200 kilohertz oscillator. It comes out of here. You filter out the 200 kilohertz, and the only thing that gets out to the speaker is your audio. Now, in very, very low cost Class D amps, they'll forego the low pass filter and they'll let everything get out to the speaker because, of course, your speaker can't reproduce a 200 kilohertz signal. Now, in a big amplifier, that can be a huge problem because 200 kilohertz is still energy transfer, and you're going to put that kind of energy into the voice coil, and that will cause problems. But in some of these smaller ones, the inductance of your voice coil will actually prevent that 200 kilohertz from harming the speaker. So it will work, and you will still hear and you'll only hear the audio. Now, another thing you have to keep in mind is this oscillator frequency itself. 200 kilohertz, it has to be a frequency that is higher than the highest audio frequency you want to pass through the amplifier. So for instance, we have 20 hertz to 20 kilohertz is the human hearing range. So you want to be able to reproduce up to a 20 kilohertz signal. If that clock frequency was too low, then it would not be able to recreate that signal. So you're going to have at least double what the frequency you need. So if you need 20 kilohertz, you would need this to be at least 40 or 48 kilohertz clock speed or higher. And even that, when you start dealing with things like harmonics and things like that, then you need to have a higher frequency. So you can see this is a factor of 10 higher. Okay, so this is a 200 kilohertz oscillator for a 20 kilohertz maximum frequency output. That ensures you're going to get clean output even at high frequencies. The ones that run at lower frequency you'll get a lot of distortion as you go up in frequency. So as you get closer to that 20 kilohertz, you'll start to get distorted waveforms. So that's what that's in there to do. And it also makes it easier to design that output filter so that the filter is not interfering in your audio range as well. It's kind of a fine line. So you're usually going to see a Class D amplifier oscillator. It'll be up in that 100 kilohertz or above. And again, like I said, the real high cost ones, they can go up in the megahertz. Now what you see here is a tiny little amplifier, and I'll just put my finger next to it for reference. That's how tiny this thing is. This is a full-blown stereo amplifier, 2-channel stereo. And it can output maybe about 2 watts, 2.5 watts per channel. And it actually is a very good amplifier. It does not have the output filter, the low pass filter, which by the way is usually just a coil, an inductor and a capacitor like this. So you have the amplifier on this side, speaker on this side. And this one doesn't even have that. It just connects directly to the speaker, and it relies on the speaker's reactive properties, to deal with that high frequency. Now, what we're going to do is we're going to look at this amplifier. And the first thing we're going to do is we're going to look at the pulse train by itself. Then we're going to look at the audio, and we'll kind of see what it looks like at the speaker. And then I'll put the microphone next to the speaker here so you can hear it. And even though it might look like a mess, you will actually it won't sound like that. So, all right, so let's get started. So first of all, I have this, and I just have a really cheap battery operated, this was a kit that I built, I bought it on eBay, signal generator. It's a function generator. And I have it set to a 400 hertz sine wave, and I have the volume turned all the way down. And when we turn this on, you'll see those pulse trains going on. Now, I have a 2-channel scope. I have one channel connected directly to the output of one side, and then I have the other channel connected to the speaker and to this other channel of the scope. So you'll be able to kind of compare what that signal looks like with a load on it and with no load on it. All right, let's get on the scope. Okay, we're on the scope, and this thing only runs on 5 volts. That's all this little amplifier needs. We'll turn it on, and you can see the blue trace is the one with the speaker connected to it. The yellow trace is the one with nothing connected to it. So you can see how that speaker actually affects that pulse train. And if you look, we're running at about 211 kilohertz right now. You see that? And what's going to happen is, as we drive an audio signal into there, you'll see this widen and narrow based on your audio signal, okay? And the harder we drive it, the more it's going to do that. So let's turn some audio on and you'll hear it. And I'll hold the microphone next to the speaker. You see what it's doing? And you can see the blue trace reacts differently to the yellow trace. The blue trace is the one with the speaker load on it. The yellow one is the one with nothing on it. So it is definitely very susceptible to the load that you're putting on it. But if you heard that, it didn't sound bad, did it? It sounded just like a normal 400 hertz audio tone. So now let's shrink these a little bit. And let's separate them on the top and the bottom here so that you can see the two signals separately. And again, this is with speaker, with no speaker. And then we're going to change our time base to be able to look at a small signal. Okay? And I'll probably have to play with the trigger a little bit. So let me get that set. Okay, now we're kind of down at a frequency where you are at a sweep, scale, your horizontal, where you can actually see the 400 hertz. Now watch what happens when I turn it on. You can just see that 400 hertz, and it is 400 hertz, you see right there? But look at all that noise on there. Doesn't that look terrible? But you can't hear all that noise because the speaker cannot reproduce that 200 kilohertz. So you're seeing all the little pulses in there, but you're also seeing that waveform. We're also messing around with the, with the sample rate of the scope and everything. But take a look at that. All right. So now let's put a filter on there. So the first thing I'm going to do is at the output of the amplifier, which is this blue wire, I'm going to put a 33 microhenry filter in there, just like that. So now we have a 33 microhenry inductor, I said filter, inductor in series with your speaker now. In addition, I'm going to go over here and I have a 1 microfarad film capacitor, and I'm going to put it also in parallel with the speaker, just like so. If I can get everything hooked up. There, just like that. And when I connect that little filter circuit, which is this, now let's look at the blue trace. What happened? Okay, and what happens when we turn our audio on now? And there you go. You get a nice looking sine wave, 400 hertz. So why did they not put the inductor and capacitor on this little board? Well, it's cost. It's cost savings. If you're just going to connect this to a small speaker, and this is only going to be a low wattage device, it'll work without it, and you won't hear all that. But can you imagine how much noise this thing is producing? And of course, if you put this inside a radio or something, this would cause a lot of noise because of all that hash and everything you're looking at. So bottom line is, that's how these work, and that's some of the pitfalls of a Class D amplifier. And that's why you have that filter, like this big amp has that filter network of the inductor and the capacitor. And this is in series, this is in parallel with the speaker. So I hope that kind of gives you at least an introductory idea of what a Class D amplifier is and what it's doing. It's not the same as your regular Class AB amplifier that we're used to looking at on, you know, when you look at these old Pioneer and Marantz and Sansui and all these classic pieces of audio gear. They don't do that. And that's why they're great big, and they have big heat sinks, and they create a lot of heat and so forth. And that's why these Class D amplifiers do not. That pulse train isn't really doing anything. It's not really drawing any current, because if you look right now, we're only drawing 9 milliamps of quiescent current at idle. And that's the beauty of a Class D amp. They run very low idle current, and they will only draw current as you drive signal into it. And that's how they work. Okay, so hopefully that clears up a Class D amplifier. And that is certainly not what is going on inside of a Carver amplifier. So the next one we're going to look at is the Class G, and I'll do that in another part. I want to keep these short, and then hopefully from now on you'll kind of know what's going on in the Carver amps when we do videos on them and so forth. So until next time, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon, because I'm going to post these two videos real close to one another, because I'm going to film them both at the same time. Take care, everybody. Bye-bye.